Right, so welcome back to advanced modeling methods, and we're going to continue obviously with the trend and the topic of modeling methods, but what we're going to change is the dimensionality of the problem. Okay, we've been concentrating on 1D problems just to demonstrate the implementation of method of weighted residuals. We implemented method of weighted residuals in different forms or classes. And we looked at how they actually led to the well-known techniques as finite differencing, finite elements, and finite volumes. Finite elements is the technique of choice, is the status quo for numerical analysis when it comes to solid mechanics. Okay, any software that you use that does solid mechanics, that does elastostatics or even elastodynamics analysis uses as its kernel a finite element solver. That's what's under the hood. Everything else is just an interface so that the program can talk to you, a graphical interface. When it comes to CFD, computational fluid dynamics, the technique of choice is finite volume methods. Now what we're going to talk about for this next part of the semester, for the next 4 or 5 weeks, is the boundary element method. And the boundary element method is not a modern technique anymore, it's not a new technique anymore, because it started in the 70s, bit of a maybe 10 years after finite elements came about. It is mathematically more rigorous than finite elements. It's a lot more elegant and it's a lot more precise. However, it's a lot more limited in its applicability. It can only be applied to certain classes of problem where the mathematics of the method allows, and you're going to see why when we go through the formulation today. So the first portion of the derivation, the formulation of the boundary element method is mathematically rigorous, but you will see that at the end you end up with a very simple form that accomplishes something great, which is reducing the dimensionality of the problem. If you have a 3D problem, it will turn it into a 2D problem. If you had a 2D problem, it will turn it into a 1D problem. So it's a very simple problem to implement numerically. Mathematically, it's a lot more convoluted, but numerically it's a lot simpler because you don't have to worry about volume meshing or anything like that if you have a 3D problem. You just worry about the surface. If you have a 2D problem, all you have to worry is about the line around it. Okay, so this is boundary elements. The story behind it is most of these people who worked on finite elements decided to go a step further, and actually most of the precursors of boundary elements were related or associated to the precursors of finite elements, either their students or themselves. Okay, either they're PhD students or they're the same people who said, well, maybe we can go a step further in the derivation. If you remember when we did finite elements from the method of weighted residuals, we took the residual minimization integral and we applied integration by parts. Okay, in boundary elements we're going to do it twice, and when we do it twice, something really good happens. Okay, something really good can happen, and we take advantage of that. So this is the story, and I'm going to tell you later why is this technique, which is very powerful, very accurate, actually orders of magnitude more accurate than any other technique, and it's also very easy to implement, why is it not more popular than the other ones? You can find commercial software that is based on boundary elements for a very small family of field problems. In acoustics, it's really good because it's an outside problem, it's a scattering problem. You can find it for corrosion problems, it's very good. Some commercial codes that rely on boundary elements. And for very specialized heat conduction problems, because heat conduction is a linear, very simple problem, and this is what we're going to use to implement the technique here in class. All right, so this is advanced modeling methods. And we're going to look at, this is lecture number 9, right? And we're going to start talking about the boundary element method. And acronym BM. All right? And as I said, well, it's not a new technique. Started in the 70s very slowly. It picked up in the 80s. A lot of people started publishing and finding ways to apply it and implement it into different field problems. In the 90s, it actually flourished, and this is when I picked it up. In the early 90s, I started publishing a lot in boundary elements. This is a good thing about non-conventional modeling techniques, that the door and the windows are wide open for you to contribute and find things that are new and actually publish. When you work on this, on things that are very established, you have to work on them minute, very fine detail to be able to yield something that is publishable, that is new. But the boundary element method allowed me the opportunity of mingling with some of the great minds in numerical methods for the best part of maybe 15 years or so, and it allowed me the opportunity of publishing a wide variety of articles and books and things like that in this area. So I still have a great affinity and memories, even though I steered away from it a little bit. So before we get into the boundary element method, I'm going to tell you that we are not going to depart from the method of weighted residual formulation. You're going to see that it actually belongs to the same class of problems, that somewhere in there in the formulation you can find it. Before we formulate it, we're going to learn two identities. One is called the Green's first identity. And these are just mathematical identities, okay? No approximations or anything like that. This is just equalities. Given the field functions P and Q, defined in a domain omega with boundary gamma, Green's, George Green. The integral of Q times the Laplace of P over the domain, whatever that domain is equal to the contour integral over the boundary of Q times the gradient of P dotted into the normal vector, the gamma, minus the integral over the domain of grad P, grad Q, d omega. And this is Green's first identity. And if you look at it closely, it is nothing more than just integration by parts. This is what it is. It's just integration by parts in space. This is u dv is equal to u times v minus the integral of v du. If you identify this, and notice that this is u, this is dv, so the integral of u dv is equal to u times the integral of dv, which is v, minus the integral of v du. So this is equivalent to integration by parts in space. Nothing more than that. It just took a few hundred years after integration by parts for somebody to realize that this could be done in multiple dimensions. All right. So, well, how can we implement this? Well, it depends on what the domain is. For example, if it's 1D, the domain is just simply a line, while the boundary gamma is just 2 points. So if this is the domain, the boundary are just the endpoints of that line. So basically this theorem or this identity reduces to a simple integration. So integration over the domain will be simply the integration from some x1 to x2 of q, the second of p dx squared, which is the Laplace in 1D. The Laplace operator in 1D is just the second derivative with respect to x. Dx is equal to, now the integral over the line is no longer an integral because there's no line, there's just 2 points. The boundary is just 2 points, so this would be simply q dp dx evaluated at x1 and x2 minus the integral from x1 to x2 of dq dx times dp dx dx. This is what happens in 1D, and I could have done dp and dq, with just the order doesn't affect here. All right. In 2D, omega is an area and gamma is a bounding line. So essentially, this could be omega, this could be gamma, and gamma is just this bounding line, and the normal vector to the boundary, outward drawn normal unit vector is just that n at any point on the boundary. So these first green identity expressed in 2D would just simply be an area integral of q Laplace of p, the area, is equal to a line integral of q graph p dot n dc minus an area integral of graph p graph q the area. And likewise, in 3D, then omega is a volume, and gamma is the bounding surface. And so we have omega, this is the surface gamma, the differential of surface, let's say a little piece here, is a differential of gamma, and the normal vector points in the outward direction. So this would be a triple integral over the volume of q Laplace of p, the volume, is equal to double integral over the surface of q graph p dot n, the surface, minus the triple integral over the volume of graph p dot graph q dv. So this is first Green's first identity expressed in all 3 dimensions. But we are going to just forget about the dimensionality and always express Green's first identity like this, where whatever that domain is, if it's 1D, 2D, or 3D, we just call it an integral over the domain omega, and whatever that boundary is, if it's just points, a line, or a surface, we just call it an integral over gamma. Okay? So we're going to do Green's second identity. So basically, apply integration by parts to the remaining integral on the right hand side of Green's first identity. So we're going to take Green's first, which looks like this in general, and we're going to take this one and apply integration by parts again, where this is u and this is dv. Alright? So that results the integral over a domain is equal to the integral over the boundary minus the integral over the boundary again of p plus the integral over the domain of p Laplace of q so this is basically two integration by parts. This is what we had originally. We apply integration by parts, we ended up with these and another integral. We take that integral and apply integration by parts, we end up with two integrals. But the consequence of these is notice that the Laplace operator was transferred from P to Q. So first it was applied to P, now it's being applied to Q. And that is something that is going to have major relevance to what we want to achieve later on. All right. Any questions so far? It's just identities. We haven't invented anything. We haven't done anything new.
The same operator.
The Laplace operator is this.
Delta squared.
Yeah, del square is called the Laplace operator. So we transfer the Laplace operator from being applied to P to be applied now to Q. Plus a couple other things. All right. So it seems that we had this, right? And now we turn it into this, which is much more complicated. So what's the purpose of that? You'll see now. Now these identities are 120 years old. And boundary elements, obviously computers didn't exist at the time of Green. But he saw some future application. I don't know, mathematicians don't think of applications, but it turns out that it had major applications. First of all, Green's first identity is the basis for the finite element method. Remember in finite elements when we took the residual minimization, we multiplied times the weight function, and then we apply integration by parts. That's basically what we do. We did integration by parts because we had it in 1D. But if you apply finite elements in 2D or in 3D, you would have to use Green's first identity, which is nothing but integration by parts. Now we're going to do it in, we're going to do it also in multidimensional. We're going to see what separates this from the boundary element method. So consider the steady, homogeneous heat conduction problem. Again, this is the problem that we've been working with because it's governed by the Laplace equation. The governing equation is the Laplace of the temperature is equal to 0. So this is the Laplace equation. So we have steady heat conduction in a medium that is homogeneous. Okay, conductivity doesn't change as a function of position, it doesn't change as a function of temperature. And it's also, there's no generation in the medium. So I forgot to say homogeneous with no generation. But we already wrote that when we were developing or formulating the other methods, for which we use the Laplace equation again. And for simplicity, I'm going to say, well, we know that x belongs to omega, omega being the domain, such that x is x in 1D, x is xy in 2D, and x implies xyz in 3D. Okay? I'm just not going to write the entire dependency all the time. I'm just going to write x. And that implies that whatever dimensions we're working on, that is x, xy, or xyz. We need also some boundary conditions. And let's say that temperature at some gamma t, at some portion of the boundary that's gamma t, is equal to some t. And let's say that minus k, the TD normal at gamma q, is equal to some q. Those are the two boundary conditions that say, well, they don't have to be that way, but what we know is that if this is the domain omega, there's a portion of the boundary that we can call gamma t, and there's a portion of the boundary that we can call gamma q, such that gamma t and gamma q makes up gamma. So the entire boundary of the problem, for these to be solvable, numerically or exactly or analytically, the entire boundary needs to be prescribed with a boundary condition, either of the first kind, or of the second kind, or even the third kind, but we're not going to get into that right now. All right. So, these boundary value problem, BVP, can only be solved exactly if the geometry is framed in a rectangular, that would mean coordinate system. That would mean either Cartesian, cylindrical, spherical, etc. Any of the 12 possible rectangular coordinate systems or orthogonal coordinate systems. That means that we can only solve this problem if it's in a square or rectangle, or a circle, or a hollow circle, concentric, or a cylinder, or a concentric hollow cylinder, or a sphere, or a hollow sphere, or a wedge of a sphere. Those are the only situations in which we can solve this problem, as long as the geometry is perfectly framed. If the geometry is irregular, if it's a triangle, we cannot do it. If we have an L-shaped geometry, as simple as it could be, we cannot do it because it's not framed within an orthogonal coordinate system. And these can only be solved by well-known techniques, such as separation of variables, and superposition, and we also have variation of parameters. We also have Green's functions method, which is also due to the same Green guy. But it's not something we're going to cover here. Okay. So, what do? If we want a solution to this problem, we resort to a numerical approximation. Okay? If we want to do finite differencing, Well, we know that we have to have a sequence of points, that it's a regular distribution of points in a counter manner. If we want to do finite elements, we know we have to kind of mesh that domain into elements and use shape functions, polynomial shape functions within each of the elements. But we're going to do something slightly different now. Instead, attempt a solution in terms of a residual minimization, something akin to the method of weighted residuals, such that. So we're trying to solve these problems. Laplace of t equals 0. And instead of solving it directly, what we're going to say is, well, the integral over the domain of some function g, which we don't know, Laplace of t over the domain must be equal to 0. All right? So,
What's that thing?
akin to method of weighted residuals. Because remember what we did in the method of weighted residuals? We took the equation, we multiplied times the weight function, we integrated and made that equal to 0. That's the residual minimization. Okay? So this g is effectively a weight function. We just don't know what it is yet. Okay? In the method of weighted residuals, if we make g equal to the direct delta function, that's called collocation. That's finite differencing. Okay? If we break the domain up into subdomains and make g equal to 1 on each of the subdomains, that's finite volumes. Okay? If we break up the domain into subdomains and then make g equals to local scope polynomials, that's called finite elements. Okay? And we integrate by parts and so on. But we're not going to do that yet. We're not going to decide what g is. We're going to leave it be. Okay?
So g is a function of x and
Xi. I'm going to explain what
Xi.
Xi is.
Okay.
Okay? Xi is x in Greek, so it's kind of another x in another dimension.
okay, just an alternative.
Yeah. Where gx of psi is a weight function to be determined later. The point psi, remember that x implies x, xy, or xyz depending on how many dimensions we have, right? If we're working on 3D, then x is xyz. I'm just, for brevity, for the sake of space though, I'm not explicitly writing all the dependencies. It's just x, space. So the point psi is known as the source point of the weight function. G of x and psi, such that psi contains xi in 1D, psi contains xi, yi in 2D, and xi implies xi, yi, zi in 3D. Same thing. All right? So we don't know what g is, but we know that g depends on the field variable, the space x, and it depends on some source point, psi. Remember in collocation, that's exactly the same thing. When you make the weight function right here, you make it the direct delta function. The direct delta function depends on x and depends on xi, right? It's a function of x. It also depends on where you collocate the direct delta function, okay? So it has two dependencies, x and the point at which you collocate it. And depending on that collocation point, we can come up with a minimization of this residual. And we're going to do something very similar. The function g, whatever it is going to depend on x, and it's going to depend on some form of collocation. It's going to depend on some source psi. All right, so now take that and apply Green's first identity. Now apply Green's first identity. And what do you get? Well, that will turn into an integral over the boundary of G times grad of T times the normal vector. I'm going to put this in a bracket, minus the integral over the domain of grad T dotted into grad G, the domain, and that's equal to 0. All right? This is the basis for the formulation of the finite element method. FEM, where G is chosen to be local scope polynomial shape functions. That's what we did. And the domain is broken up into spaces and so on and so forth. Okay, and we have all the fluxes. These are the fluxes multiplied to the polynomials are integrated over the boundary. All right. Now integrate the domain integral. Remember, this is a boundary integral, right? And this is a domain integral. Integrate the domain integral in parts, leading to Green's second identity. Remember that Green's second identity is just basically Green's first identity twice. So basically, this one remains G times the grad of T dot N gamma minus T times the grad of G dot N the gamma plus the integral over the domain of T times the Laplace of G d omega is equal to 0. So we have something simple, which was this, and now we turn it into that. We have this is equal to 0, now we turn it into that, which has much more, or many more integrals now. It has boundary integrals and it has another domain integral. But notice, sorry, we can see, we turn that into this.
What is that over omega?
Yeah, this is over omega. It's d omega. All right? But what we managed to do is transfer the operator, which is originally being applied over t, now we transfer it over g. Let's see what we can do with that. All right? Oh, by the way, these right here, these term in brackets is just the TDN. And this term in brackets is just the GDN. Remember that the n is just a normal derivative. So for simplicity, we're just going to say that that's dt dn and that's the gdn. All right. Now, what do we do? Remember that g, we don't know what it is yet. It's a weight function, but we haven't chosen the weight function. Now we're going to pick the weight function. Now, select the weight function g of x and psi such that, so instead of explicitly choosing the weight function as polynomials or whatever, we're going to choose that the Laplace of g is equal to the negative of the Dirac delta function at the source point xi. So notice I am not selecting the Dirac delta function. I'm not selecting the weight function g. I'm selecting how it behaves. Okay, what constrains it. So notice that the weight function g of x and psi is not chosen explicitly, but rather as the response to the collocation of an infinite impulse, which is, as we know, the Dirac delta function at the source point psi. And hence g is a function of x and psi. Okay? For finite differencing method, remember we chose g to be the Dirac delta function. We chose a weight function w to be the Dirac delta function. Now we're choosing the Laplace of g to be equal to the Dirac delta function. Alright? And the negative sign is there for a reason, I'm going to tell you later, but it doesn't matter. You can make it positive or negative, you just end up with plus or minus sign somewhere else. So this leads to the integral of g dt dn gamma minus the integral over gamma of t dg dn gamma, and now we have a minus the integral over the domain of t times the Dirac delta function, the omega is equal to 0. This is what we have so far. All right. So remember what a Dirac delta function does inside an integral?
Takes the function basically.
It takes the function out. It's called the sifting property. Because the Dirac delta function is 0 everywhere except at the point of impulse, which is infinity, there. The Dirac delta function has the area property that if you integrate the Dirac delta function, you get 1. It has an area, a unit area. The integral of the Dirac delta function is equal to 1. Or if you integrate any function multiplied times the Dirac delta function, then the result of that integral will be the function evaluated at the source point of the Dirac delta function. Okay, it sifts it out of the integral. It's called the sifting property. Okay, so this integral will disappear. It will go away. It will basically be t of psi. That's it. Except when that point psi is outside the boundaries. If it's outside the boundary, that integral is 0 because the source point is outside the integration domain. How about if the source point psi is somewhere on the boundary of this integration domain? Then the integral will only see 1/2 of the Dirac delta function. Okay? If it's somewhere on the boundary, you only see 1/2 of the Dirac delta function, so you'll get 1/2 of t. You see that? Okay? So recall the sifting property. let's rewrite that, recast that. We call the shifting property of the Dirac delta function the integral over a domain of t of x times delta of x and y, the omega is equal to c times t. And that c is just some parameter that depends where the source point xi is, such that c of xi is equal to 1 if xi is within omega, right? Is 1/2 if xi is somewhere on the boundary, and is 0 if xi is outside of the domain omega. Okay, this applies to 1D, 2D, or 3D. It really doesn't matter. The Dirac delta function is just a unit impulse that is 0 everywhere except when x is equal to the source point when it shoots to infinity. But it has that very nice property. So if we use this in here, on the residual minimization formula, what we end up with is C of psi, T of psi, is equal to the integral over the boundary of g of x and xi, dt dn, minus the integral of t of x times dg dn d gamma. Right? And that is called a boundary integral equation. It's an equation that relates the temperature anywhere, because I can put psi wherever I want to, right? The temperature anywhere to the flux and the temperature on the boundary only. That's why it's called a boundary integral equation, not an integral equation. So if I know the temperature and the flux everywhere on the boundary, not just a part, I know the temperature, and another piece, I know the flux. I need to know the temperature everywhere, and I need to know the flux everywhere on the boundary, which is an overimposed problem. But if I were to know that, I can use this expression to find the temperature anywhere I want to. That includes the boundary, that includes the interior. So the problem is solved, okay? Except for something. First, we don't know the temperature and the flux everywhere. We know the temperature somewhere and the flux somewhere else, okay? And also, we don't know g yet. We know that the Laplace of g is equal to the Dirac delta function, but we don't know what g looks like. We need to solve for g, right? However, this is an exact expression. We haven't done anything that is approximate. This is an exact relationship that is equivalent to the Laplace equation, okay? This expression is known as, well, we're not seeing the whole thing. It's known as the boundary integral equation, BIE. And it forms the basis for the BEM, for the boundary element method. It constitutes an exact relation between the temperature anywhere any points I, and the temperature and flux on the boundary. Yeah. So if we know temperature and flux on the boundary, then we can know the temperature everywhere, or anywhere. Okay. So, what is G? We have that expression, and we know that it relates temperature and flux on the boundary to the temperature anywhere we want to, but we still need to know what G looks like. Now let's solve for G. What does it look like? Remember that the only thing we know about G is that the Laplace of G is equal to the negative of the direct delta function. So somehow we have to extract G out of there. And it seems more difficult than the original problem, right? Because the original problem was Laplace of t equals 0. So why we made all this transfer identity to end up with something that has some integrals, to end up with something where we would need to have a solution to a problem that is more difficult than the original one? Well, for one, this problem doesn't have boundary conditions. See? And it's not a field problem. There's no field. This is a free space problem. That problem should be valid in infinity. If I place a direct delta function here, that should give rise to a g function, a weight function, anywhere towards infinity. Anywhere all the way to infinity, even close to the source point. Okay? So, although these problems may seem more complicated than the original one, that is the Laplace of t is equal to 0, it differs from it by the fact that it is a free space problem with no boundaries or boundary conditions. So G must be valid everywhere. Now, to solve this problem, first recognize that the effect of the impulse, so if there's an impulse here, let's say that this is a 3D space and I put an impulse here, an infinite impulse of temperature, a direct delta function right here, that impulse will propagate spherically, okay, radially symmetric. If we're talking about a 2D plane, and I put an impulse somewhere on the plane, that impulse will propagate radially symmetric to the point, to the source point, right? Whatever it is, 1D, 2D, or 3D, it will always propagate radially symmetric. So the effect of the impulse is radially symmetric as the signal propagates radially from the source point Okay. So, if we're talking about a 1D problem, and this is x, this is what psi looks like, and this is what the infinite impulse would look like. It would be 0 everywhere except there where it's infinity. And I'm kind of attenuating what it does, because remember, it's perfectly 0 and in the limit when x goes to psi, and it's infinity at the limit when x goes to psi. 0 everywhere else. And in 2D, so let's say this is a so the source sort of grows radially. Well, the signal propagates radially from the source point. Okay. That is, if you plot the derivative of the function in 3D over a 2D plane, the Dirac will be in the z-axis. Okay? If you plot Dirac at a point xi, it will look like 0 everywhere, and then it shoots up at that location. But if you attenuate it with those algebraic expressions that approximate the derivative of the function, remember that exponential of r squared and so on, then it would actually look like that. All right. Now, let's focus on 2D. Let's do this on 2D, or in 2D. So, in 2D we know that x is xy, and xi is xi, yi. So, the Laplace of g is equal to the derivative of the function of x and xi. The Laplace in polar coordinates, r theta will simply be 1 over r d dr r dg dr plus 1 over r squared, the second derivative of g is equal to minus the derivative of the function, such that r is equal to x minus xi squared plus y minus yi squared. Square root of that. It's just the Euclidean distance between any point x, y, and the source point xi, yi. Remember, we're defining the polar coordinates with the center right at the source point xi. Right? Now we know that if the impulse is radially symmetric, we expect the function to also be radially symmetric. Right? So if delta x and psi is radially symmetric, then g of x and psi should also, or must also, be radially symmetric. Therefore, d theta should be equal to 0. There's no theta variation of g. So the equation that we need to solve for is just simply, therefore, 1 over r ddr of r dgdr x and y is equal to minus the Dirac delta function. Again, r is defined like this. So these are polar coordinates with the center at the source point. All right, now we need to solve that equation. To solve this equation, first, look far away from side, and then close to side. All right? So the first part, away from the source side, the Dirac delta function goes to 0, right? When x is away from xi, far away from the impulse point or from the source point, there is no effect of the Dirac delta function. So basically you're looking at solving this equation. Can we solve that equation? We can integrate a couple times, right? So we can send the r over to the other side and say that this is just simply ddr of r dgdr is equal to 0. Now we can integrate, and this is r dgdr is equal to a. Now we can say that the gdr is a over r, and now we can say that g is equal to a log of r plus b. Right? Now for simplicity, let's let b equal to 0. Let b equal 0. That is one acceptable solution. Also because when we introduce this back into the boundary integral equation, having a b of 100 or 0 really doesn't matter because it will cancel out. One is positive, the other one is negative. So the b will not make any difference in the overall solution. So what we have so far is that g of x and y is equal to a log of r. Recall that r is equal to the square root of x minus xi squared plus y minus yi squared. Right? Now we're going to do this to find that other constant a close to the source point side. So as x goes to xi, delta of x and xi goes to infinity. So we go back to this. And what we're going to do is concentrate, focus really close to the source point side. And integrate this expression over a circle of radius r as r goes to 0. So we're going to shrink that circle to the limit when r goes to 0. So basically the limit as r goes to 0 of the integral of this is equal to the negative of the limit as r goes to 0 of the integral over, this is omega c, the Dirac delta function. Now the integral of the Dirac delta function, as small as this circle could be, is 1, because it contains the source point. 1. Recall that surrounds psi, because the radial coordinate system, or the polar coordinate system, is defined around the source point. So basically, we have the limit as r goes to 0 of the integral over the circle of the Laplace. I'm going to break it up into the divergency of the gradient of g is equal to -1. All right? Now I'm going to apply Gauss divergency theorem. This is the divergency of a function. And that's why I purposely broke the Laplace into the divergency of the gradient. That's how the Laplace is defined. Apply Gauss's divergency theorem. And this will be the limit as r goes to 0 of the integral over the circle of grad g dot n d gamma is equal to -1. All right? So basically we have a source point. We have a circle around it. We have r, and around that circle we have the normal vector, which in radial coordinates is just simply ER. The normal vector to a circle always points in the radial direction. It has no tangential direction. Okay? So, d gamma is equal to r d theta, when we turn this into a circle integration, such that theta goes from 0 to 2 pi, and the grad of g in polar coordinates is the GdR in the r direction, plus 1 over r, the g d theta in the theta direction. But it really doesn't matter because g doesn't depend on theta. So when we implement this in here, we have this limit as r goes to 0 of the integral from 0 to 2 pi of the GdR ER dotted into ER times r the theta should be equal to -1. Right? So remember that g is equal to a log of r. Therefore the GdR is a over r. Okay? So such that the GdR is equal to a over r. this is the limit as r goes to 0 of the integral from 0 to 2 pi of a over r. The er and the er cancel out, times r d theta is equal to minus 1. R and r cancel out, and what we end up with is the limit as r goes to 0 of 2 pi a is equal to minus 1. Now the limit goes away because there's no r, and simply a is equal to minus 1 over 2 pi. And plug that back into g. G of x and psi is equal to minus 1 over 2 pi times the log of r. This is in 2D, such that r is equal to the square root of x minus xi squared plus y minus yi squared. And this is the well-known Green's free space solution. This expression is known as the Green's free space solution to the Laplace equation. Or basically to the Laplace equation when it's perturbed by a unit impulse or an infinite impulse at psi. Right? If we follow the same process, following the same process in 1D, the Green's free space solution is x minus xi, the absolute value divided by 2. In 3D, the Green's free space solution would be 1 over 4 pi r such that r is equal to x minus xi squared plus y minus yi squared plus c minus yi squared. So now we have the Green's free space solution. This is not to be confused with Green's functions. Okay? Green's functions due to the same Green, but there's another technique to solve differential equations where the function is found specifically for the problem. It's constrained with homogeneous boundary conditions, but it is constrained to boundary conditions. In this case, it's a free space solution. There's no boundary, there's no boundary conditions. This is what happens, this is what you get if you perturb the field with the derivative of the function at any point psi. If it's on a plane or in 2D, you get the log. If it's in 3D, you get that decay. And as you can see, this right here is a singular response. If you put a derivative of the function anywhere here, well, the derivative of the function is infinity and 0 everywhere else. What you'll get is you get a more attenuated decay, but it's infinity at r equals 0. It's infinity right at the source point, but it decays a lot slower than just going from infinity to 0. See? And in conclusion, let's just finish up today. So let's recast the BIE back to the BIE, where we have C of xi, T of xi is equal to the integral over the boundary, gamma, over the entire boundary, that's what this circle is here, minus the integral over the entire gamma of t, dg dn, but now we know what g is, and therefore we know what the g dn is. now that g of x and xi and the g dn of x and xi is known, the BIA yields the solution t at any point psi as a function of boundary values of temperature T and flux dTdn. So it's just a boundary only relationship. If I know what the boundary looks like, which I should know, right? Even if it's a triangle, now we don't have a problem because I can integrate around a triangle. If I had the T and the dTdn everywhere, I can know the temperature anywhere I want to. And that's an exact relationship. This is an exact relationship. We haven't introduced any approximation whatsoever, as opposed to any other numerical technique that relies on approximations, whether it's tessellation of the domain, subdomains, collocation, usage of polynomial shape functions. Up until this point, we haven't introduced any approximations. This is perfect, it's analytical, this is exact. That's why the boundary element method is more precise than other techniques. But remember, now we're limited to this point to the Laplace equation, which governs steady heat conduction, it governs acoustics or acoustic scattering in the frequency domain, it governs maybe ideal fluid flow, and just this very small subset or class of field problems that we can tackle with these expression right here. All right? Any questions? Well, that's it. When we get together on Thursday, we'll introduce approximations to this. All right?